In Hwa much waste is generated every day, making it a hassle for our fellow cleaners. Such waste includes plastic, food, and many others. Today, we're going to specifically focus on plastic waste generated in the canteen with our proposed system that ensures better treatment and disposal of plastic, and also to reduce the waste and minimize carbon emissions as well as reduce energy. One of the primary reasons for plastic waste is the high volume use of single-use plastic items by the drink stall. Many students purchase such drinks and throw them away after finishing it, resulting in a large accumulation of plastic waste in a short time. These plastics are contaminated with leftover liquids or food residue, making them unsuitable to recycle if not cleaned properly.
Our proposed system begins with source separation at the utensils collection zone, where we will set up different transparent bins, each one for food waste, plastics, drink cans, as well as a recyclable bin. This is for easier identification for students. We are going to only focus on the plastic bin for this video, which will be placed beside the closest sink near the drink stall for efficient disposal.
Next to the plastic bin, we will install a cup wash sprayer for students to rinse their plastic bottles and cups before disposing of them. This design is simple and convenient for students to use, making washing the cups second nature for the students. Since contaminated plastics are difficult to recycle, they are often sent for incineration, which wastes energy. To understand why contamination causes such problems, we need to look at how plastics are recycled.
According to the Singapore Environment Council, Singapore uses about 1.76 billion plastic items each year, including 467 million PET bottles. Only 6% of this was recycled. PET is recycled via mechanical reprocessing to new bottles, fibers, films, or engineered products. As mentioned earlier, PET cannot be properly recycled with contaminants. Such contaminants include food residues such as sugar and oil, which can reduce polymer quality during extrusion and lead to charring, making them unable to be recycled because they pose a risk of contaminating other plastic waste when sent for recycling.
Water present in the plastic cups might also cause hydrolysis, where water molecules interact directly with weak bonds in the polymer backbone such as esters and carbonates. The water molecule splits, inserting a hydroxyl group OH- and a hydrogen atom H+ into the polymer chain, breaking it into smaller chains or monomers. This shortens the polymer chains, disrupts the structure and reduces the material's strength, durability, and overall quality. As a result, recycled plastic cannot be reused for high-grade applications like bottles.
In material recovery facilities, contaminated plastics waste a large amount of mechanical and electrical energy only to be rejected, making this energy output useless. For PET to recycle, it must be melted down at temperatures around 250 to 260 degrees.
If a batch of crushed plastic arrives at a material recovery facility soaked in leftover liquids, the facility's heaters must first expend vast amounts of thermal energy just to boil off and evaporate that liquid, before the plastic can even begin to melt. MRFs use hot washing processes to clean plastics. Sticky, sugary residues from canteen drinks contaminate the wash water much faster. This requires a facility to continuously heat fresh water and run industrial pumps for longer cycles, draining electrical and thermal energy.
Hence, our solution aims to minimize the risk of contamination by encouraging students to rinse their plastic cups and bottles with water before disposing. Next, we propose that at the end of every single day, the plastic cups and bottles are collected as a whole. Uncrushed plastic bottles have a very low bulk density because they enclose mostly air. By compacting them, the volume dramatically decreases while mass remains constant, effectively maximizing the bulk density. This optimizes the transport truck's volumetric capacity and thus minimizes the carbon footprint per kilogram of recycled material. We have also considered a different solution to ensure only clean plastics are recycled. We tried a verification system for the bins to reduce human error, which involves a trapdoor mechanism based on mass, where bottles that are still filled with liquid are too heavy to pass through. However, it may not be the most practical solution as it could be costly to install and maintain. And without a standardized mass for dry bottles, disposal during peak periods would be slow due to bottles getting rejected. In conclusion, our solution doesn't have to rely on complex engineering or human nature. It just applies fundamental concepts of physics or chemistry to reduce waste and prevent contamination in order to make bulk recycling viable.